Hello everyone, in this session we are going to discuss a brief about algorithm, its characteristics and the concept of efficiency. We will be discussing these points in detail regarding introduction and the features of algorithm, parameters which affect the performance of algorithm and how it can lead to complexity analysis. So let us start. If we talk of introduction, the first question comes in our mind: what is the need of algorithm? If we talk of algorithm, we need to talk of problem statement. Problem statement is about stating effectively what needs to be done. Once it is ensured that this particular problem needs to be solved, like any programming problem is given to us, this is the very basic step that needs to be clear. If we are not clear with the problem statement, we are not able to write the logic for the algorithm or logic for the program. Once it is done, then we can move to the algorithm. We need algorithm to properly understand the solution before directly moving to the programming part. Suppose if we directly work on the program and we are not successful, and that failure is because of not understanding the solution of the problem. So it would be better if we can work on the solution first without using the computer resources like any programming language or hardware. So that algorithm gives a way of understanding the solution of a given problem in manual manner, so that we can write a sequence of steps that leads to the solution of the given problem. Even we use algorithm to give a standardized way of expressing the solution of the problem and to have a basic idea of the performance of our code if we are going to implement the algorithm. Okay, so that way we compare that program and algorithms, although they are complementary to each other, but they are different. When we talk of algorithm, we are writing with the pen and paper, or we are writing in the notepad or text editor the sequence of operations. Okay, and actually when this is justified that by these sequence of steps we can solve the given problem, then we move to the programming part where we actually implement the problem. Okay, we use certain hardware resources at that point of time, we use certain programming environment for execution. So before actually implementing program, we prefer to complete the algorithm, so that at runtime our focus will only be on the syntax part, how to use the particular programming, and the solution or the logical solution is already available with us in the form of algorithm. So what we call it as an algorithm? It's a step-by-step description of solution to the given problem, so that it could be easily and directly implemented in any programming language, where there will be less focus on the logic but more focus on the given programming language, how to write that logical step that we defined in the algorithm part. Okay, so let us move. We cannot call any steps as a algorithm, so for that there are some standard guidelines given which we need to follow to ensure that whatever steps we have mentioned as a solution to the given problem are correct. So we need to follow these guidelines or characteristics for defining the algorithm. So there should be input. It's not mandatory that we'll always have input. Sometimes without input we give output in particular problems. So this definition gives that there should be 0 or 1 input to the given algorithm, depending on what problem we are going. 0, 1 or more input depending on the problem given to us. That is the first characteristics. Obviously in special cases we can have 0 input, but there would be 1 or more inputs. Okay, output. Although we may not have input, but output should always be there. Minimum 1 output should be given by the algorithm. If there is no output, then why we are working on the algorithm? Actually, we need to solve a problem, and that problem needs a solution. So that solution could be minimum 1, and it could be more than 1 depending on the problem. Okay, this is the next characteristic. Another one is definiteness. That means like if we are going to implement matrix multiplication, we cannot simply write that take 2 matrix, multiply it and then give result. These are not the steps. We need to give those minute steps. They should not be so small or should not be so big that we cannot define it or we cannot actually understand it. So there should be unambiguous statements that should be clearly defined in the algorithm so that we can understand the basic steps. Okay, and that could be easily and directly converted to program. Okay, so that is required. Third property, definiteness, unambiguous statements of the algorithm. We should write the sequence of steps in such a way. Next is finiteness. See, we are given a problem to solve and there should be a solution, but it doesn't mean that we mention certain sequence of steps which are not countable, like infinite number of steps we can't give. Our algorithm should terminate at some point of time. At the last it should give the output. So this property explains that whatever sequence of steps that you are going to follow, it should terminate after a fixed number of time and then it must provide the output. Okay, so that's why this is the desired characteristic. And next is effectiveness. Suppose we write in a sequence of instructions, sequence of steps. Steps may give some output, steps may be finite, or every step could be definite, like it should be unambiguous, error free, but it may not be effective. Effective means the step which we are going to write is not having any contribution to the solution of the problem. So whatever steps we are giving, that must be effective. Every small or large step, whatever sequence of steps we are mentioning, should move towards the solution of the given problem. It should lead to the solution of the problem. So effective, finite, definite steps we should mention in the algorithm with the output 1 minimum in the mind, and there could be 0 or more input depending on the given problem. Okay, now once we have written an algorithm for a given problem statement that we are going to implement, how to compare that two algorithms are same, like two solutions that we are giving written with different number of steps but giving the same output with same input, which one is good and which one is not good. So at that point of time we need to focus on the concept of analyzing the algorithm. Okay, because we need to find out the best algorithm so that there should be minimum time taken by the execution and minimum space required to store those instructions mentioned in the algorithm. So that is important. So all other parameters on which we analyze the algorithm are related to these two basic parameters, time parameter and space parameter. Time parameter means although we are not actually implementing the algorithm, but we take an idea as a functional measure that if we implement this given algorithm, how much expected time would be taken by a specific machine. I am using the term specific machine because obviously it will depend on the particular hardware on which we are going to execute the given sequence of steps. Okay, so that time parameter is the first parameter on the basis of which we compare. We get a rough idea for very large input if given to the algorithm, so that we can calculate the timing, although this time will depend on the given hardware on which we are executing. Space parameter again, how many instructions are there, how many variables we are using in the given algorithm, how many times particular instruction is being executed, whether it is using the static memory, fixed amount of memory, or it varies from execution stack, like how many times it executes during runtime. So depending on that, different algorithms may take different memory, and we analyze the algorithm on the basis of this parameter as well. We'll discuss in detail about this time and space parameter in the next video, but at this point of time you just need to understand that performance of algorithm revolves around these two parameters, where time is related with the expected execution time by the machine, which again depends on the sequence of steps that we are writing in our given algorithm, and space parameter also depends how many lines or how many instructions we are going to write in the given algorithm, and how much memory is required for execution. So these terms reflects the space and time parameter for given algorithm. We'll take an example on this, and in detail it would be discussed in the next video. So complexity analysis of algorithm, if we talk of, initially what we do, we devise the algorithm, like we design the algorithm according to the given characteristics that we mentioned. Once it is designed and we make sure that all those guidelines characteristics are followed, we validate. Validate means the algorithm that we designed is actually giving the expected output for which we designed it. It's validated. Once it is validated, we may have validated different algorithms for same problem. In order to compare the performance, we do analysis on the basis of time and space parameters that we discussed. So analysis of algorithm, as already stated, we need to focus on the time, but time in a sense that we can give a generalized view of the time independent of the given hardware. For that, we try to find a mathematical modeling of the given algorithm which express the growth of the time as we increase the input. Okay, that needs to be determined as one of the parameter for analyzing the algorithm. Again, it helps for judging the quality of the algorithm, like many students may write different solutions, which one is better. On the basis of this we can compare, and further in detail we can do the complexity analysis. Let us take an example on this, how we determine that a given algorithm will take more time or it will take less time. In that case, we estimate certain things, okay, and those certain things we are estimating because we want to perform these activities in particular scenarios. The first thing that may trigger the need of analysis is to estimate the resources to run the algorithm. Like if we have certain limited hardware, can we execute this given algorithm we are going to design on this hardware? And if it is not available, how much more hardware we need to purchase? That kind of requirement we can estimate. Okay, how much largest input that we can provide to the given problem? Sometimes we are going to sort certain elements. Can it sort only 10 numbers, or we can sort 50 or 100 numbers? So that depends on the given algorithm, and again on the given specification of the machines on which we are going to execute. And different algorithm, again we can compare the efficiency depending on whether it is taking less time, more time, less space or more space. Okay, and if some part of the code is taking more time or most of the execution is being done by that part of the code, we can focus on particular portion if we are aware of the complexity. Okay, and for different scenarios we can choose different algorithm because of the analysis available with us. So these are all things which trigger us to do the complexity analysis. Suppose we are given an algorithm to find largest of a given list of numbers. So this is the pseudocode, simply an algorithm you can say, where a high level description of the solution is given, we are passing the array A and n number of elements, and what we do is we initialize with the first element as the current max. This is assumption, and this assumption we are going to update every time after this condition is checked. So if A of I is greater than current max, that means our assumption is wrong, so we need to update the new current max, and that new current max becomes A of I. In that case, return current max. So this is simple code. Here what I am trying to quote here, that how we can estimate the complexity of this algorithm. The basic idea is to identify the basic and primitive operations in the given algorithm, the sequence of steps for finding the maximum of given array elements. So how we identify that? We focus on how many times a particular expression is being evaluated. Is there any assignment statement? Is there any function call in the code or the algorithm? And is there any return statement? Such kind of basic or primitive operations are identified, and they are calculated that how many times they are being executed. So in terms of these expressions, in terms of these operations, we find a mathematical function, and that function reflects the complexity. A kind of count of such operation. If it is more, that means it will take more time. If it is less, it will take less time. Okay. So let us try to calculate this value for the previous program. Suppose this particular indexing and assignment takes a unit time. This unit time for this assignment I am assuming to 1 unit. It could be any nanosecond, picosecond, but I am taking it as unit, 1 unit. Now this particular loop executes for certain number of times. It will execute for n times, including this last failure condition, n times. What is n? How many times or how many elements are there in the given array? Depending on that, this for loop will execute. If there is only one element, it will run only once. There is more than one, so whatever is the value of n, according to that, this n is being given. Now every statement inside this for loop will run n minus 1 times. So I am giving this n minus 1 units of time for execution of these two statements, and finally this increment counter again happening in this loop, so n minus 1 time, and this return statement will take constant 1 unit of time. So this particular instruction and this particular instruction is independent of the size of the input, and other all operations are depending on the size. So our main idea is to identify the input size dependent operations, because if the value of n is very large, then these are the only operations that we need to focus upon. Okay, so anyhow we sum up all these operation count, 4n plus 2 minus 3, that will be 4n minus 1. So in later analysis we will see that these multiple of this n and or minus 1 constant are very ignorable in compared to the value of n, because the value of n is going to be very large for this kind of analysis, where it would significance of this 4 and minus 1 would be very negligible. So in that case we can say that time will vary in proportion to n. As we increase the value of n, accordingly this complexity of this algorithm will vary. So in last example, as we have calculated, there are 4n minus 1 operation. Here we assume that primitive operations, and those primitive operations could be slower or faster. Some primitive operation may take less time, some primitive operation may take more time. Depending on that, I am taking two parameters here. First is a, assuming that it is the time taken by the fastest primitive operation, like it could be the small operation or on the high-end machine we are executing, and b is the time taken by the slowest primitive operation. For this particular number of steps, the minimum time for this algorithm would be a times 4n minus 1, and maximum because the number of operation multiplied by the largest primitive operation time, single largest primitive operation. So b times 4n minus 1. So anyhow this time is going to vary between these two factors. So we have a basic idea of the time estimate, and that too when number of input is very large, the value of n is very large. In that case, actually we try to bound the growth of the given complexity inside some function. We'll see in detail about these functions using asymptotic notation in the next video. So just to give a basic idea that what should be the minimum time for the given algorithm that we try to calculate, and the maximum time that a algorithm can take, like best case, worst case and average case analysis we'll see in detail as well. That kind of analysis we perform for given algorithm. This slide shows the effect of input size on different algorithm. Just like we calculated 4n minus 1, we can calculate these functions for different algorithms implementation for different problems. So if we calculate the number of primitive operation function as log n, that is assumed to be better, because if we increase the value of n from 1 to 32, the effect on the time is very negligible. Like it goes from 0 up to 5. For 32 input size, it takes 5 units of time, because log n represents the overall function in terms of primitive operation. So n log n, if any algorithm is calculating this much primitive operation, in that case for n is equal to 32, which is again a very small value, for this small value only it is taking 160 units of time. If we go to n square calculated primitive operation, it is 1024, and see in case of 2 raised to power n, it is a very big number. So this much units of time that algorithm requires, like this, if we have a solution to same problem with different time complexities, then you can see which one you will choose to finally implement this log n complexity. That's why we talk of complexity analysis in algorithm, and so that we can choose the best algorithm out of the given set of solutions for the same problem. Okay, so such analysis will carry on in the form of asymptotic notation in the next video. Just to give a basic idea why we do go for asymptotic notation, we'll see certain examples on this. Till then, thank you.